Welcome back. So let's pick up from where we left over in our last lecture. So in our last Friday's lecture, we get started talking about classical mechanics, and we, refreshed your memory on the concept of work, which is a path integral. And we discussed about the total work done on the system, assuming it's a reversible process or a super slow process. And at the end of our last lecture, we went over a quick demonstration in what does it mean by line integral or a path-dependent function, right? So depending on which path we take, the work that's being done on the system can be very different. So we left one example question we can work on together. So in this case, for example, we have a non-ideal gas that is heated slowly and expands reversibly. So remember, whenever we see a system that's undergo a slow expansion or contraction, basically what we're saying is we can use the equation W reversible equals to negative V1 to V2 PdV. Right, so this problem effectively just a plug-in number, but you want to be able to know what equation to use in order to solve for this problem. So that's work. Now, before we talk about the first law of thermodynamics, we have one more path integral we want to define. So that is heat. Now, heat is a concept that's commonly misused in all kinds of places. So let's just start from zero, like forgot everything you know about heat, and then we'll look at heat as a property. So in this case, like work, heat is a key path integral or line integral that we will be using in thermodynamics. We will have more equation of heat, but if you think about the most simplistic definition of heat that you probably learned in high school, what we have, imagine you have a bottle of milk that is originally at room temperature. You put it into a cooler, which is at initial temperature 4.0, and give it enough time when it's at the final temperature. We have both of the milk and the cooler to be at like 4.1 degrees Celsius, right? So in this process, we can have the heat or we write it as Q. So that equals to, M1C1 T final minus T1 equals to negative of M2C2 T final minus T2. It doesn't matter which one is T1, which one is T2. Just know the amount of heat that's given from the milk to the cooler is the same as the amount of heat absorbed by the cooler from the milk. It just depends on which one you define as a system. But nevertheless, instead of looking too much on how to do this equation, one of the things we want to keep in mind is that, in here, we have the heat, and then we have like T final minus T initial. So that tells us, like work, heat in thermodynamics is a property that is only meaningful when we are describing a process or we're describing, say, the temperature change, right? So heat, like work, is a process that's only meaningful talking about a process. All right, so say if we have a cup of water at certain temperature, without any process defined, that thermodynamic state itself doesn't tell us what is the heat of that cup of water. All right, so in here, we have the most simplistic version. We have heat equals to mass times heat capacity or specific heat capacity. which is a property of a certain material. And at constant pressure, let's say, assuming we have constant pressure, we can rewrite that equation as the infinitesimal amount of heat, or the Q with a subscription of P. So whenever you see a subscription of P, it tells us this is the heat, or this is the function at constant pressure. We'll see that in other applications as well. So that is defined as mass of the object times the specific heat of the object at constant P and dt, or the infinitesimal change of temperature. Right, so if we take the integral, we have a way to calculate QP. And thus equals to the integral between T1 to T2 times mass Cp dt. And this is, say, we have a closed system and constant pressure. Now, in here, one of the things to keep in mind is that our Cp might be a function of temperature. So you cannot directly assume to take it out. Right, so for example, in a true and false problem, let's say we have like Qp equals to mCp delta T. Like, is this statement true or not at constant pressure and closed system? So the answer is this is not a true statement, because our Cp, or the specific heat at constant pressure, can be a function of temperature, and thus you cannot take it out in the integral without knowing it being a constant. And let's look at the problem together and see what does that mean, right? What exactly does it mean? So this is an example question, 2.12. Let's read it together. It looks very long, but we can read it. It says, specific heat can be measured in a drop calorimeter. Here, a heated sample is dropped into the calorimeter and the final temperature is measured. It gives you the experimental setup of a drop calorimeter. So we can drop, like, say, 45 grams of a certain piece of metal at 70 degrees to 24 grams of water. And it's telling us the heat capacity of water we can assume as a constant, which is 1 calorie per gram per degree Celsius. And the temperature of the water, initial temperature of the water is 10 degrees Celsius, and the final temperature of the water is 20 degrees Celsius. Ask us to find out what is the specific heat of the metal with the initial temperature of 70 degrees Celsius. And then the second question asks how much heat is flowed to the metal, from the metal to the water. So we can do that together here. So in this one, we're given several pieces of information. So remember, we have the previous example. So Q equals to the mass of your metal times the heat capacity of your metal at certain temperature, which is the T metal minus the T final. So in this case, when we're referring to the heat capacity of the metal, we're saying, hey, we're treating it as a constant because we're only taking the measurement for the metal initial temperature at 70 degrees Celsius. We'll go to the hint later on to see what exactly does it mean by the heat capacity as a function of temperature. So right now we're treating that as a constant. And this equals to the mass of water times the heat capacity of water, which we're treating as a constant, times the temperature, the final temperature minus the temperature of, initial temperature of water. Right, then this problem is effectively just plugging numbers. And again, the reason these two terms are equal is because in this drop calorimeter, there are only two things exchange heat from one the other, right? So the amount of heat transferred from the metal to the water must equal to the amount of heat absorbed by the water. So that's, yes.
Can you explain why we're doing T metal minus the final temperature?
Well, we're talking about the change here, right? So it's always final minus initial, yes. But in this case, when we're looking at metal as our system, now the system is transferring heat into the surrounding. Now in this case, this should be the negative metal, negative water, which is surrounding, of TH2O minus final. I'm just taking the negative inside that parenthesis. And then this one just becomes a plugging number. So this one, the metal, mass of the metal is 45 gram times the heat capacity of the metal times the temperature, 70 degrees Celsius minus 20 degrees Celsius equals to mass of the water, 24 gram times the heat capacity, which is 1 calorie per gram per degree Celsius times 20 degrees Celsius minus 10 degrees Celsius. And our first part of the question is asking us to solve for the heat capacity of the metal, and we can get that to be C metal equals to 0.107 calorie per gram per degree Celsius. So as you can see, reading the problem together in the note, right? So in this problem, we're taking the measurement once at 70 degrees. Now imagine we can change that 70 degree to higher or lower temperature and plot what we get about the specific heat of the metal as a function of the initial temperature of the metal to get a relationship between that specific heat and the initial temperature of the metal. So that's how that's how scientists set up experiments to find out a relationship between the specific heat and the temperature. The second part of the question is very straightforward. It's just asking about the heat that's being transferred. So that's effectively the numeric number you can solve here. All right. Any questions on heat before we move on to lecture 4? Again, this part looks very straightforward. We'll come back and revisit the concept of heat later on. But the key take-home message is that heat and work, these two are the two line integrals or the path-dependent functions we use in thermodynamics. Again, they're path-dependent, meaning that we cannot solve for their value if we do not know their path, right? If we do not know how they go from A to B. Alternatively, we have other thermodynamic functions like state functions, right? We talk about pressure, volume, and temperature. So say the thermodynamic state are the same as long as their macroscopic thermodynamic state functions are the same. Okay, any questions before we move on? No? All right, yes?
Can you please repeat the bottom part that the statement of the equation you wrote is why is it false?
This one? So if you think about why this one is false, this one basically says you can take Cp and mass out from the integral and treating them as constants, right? But the fact is our specific heat, even at constant pressure, our Cp is a function of temperature, right? So you cannot directly take it out unless we specify Cp is a constant independent from temperature. All right?
How come, like, in this case,
This one, we're not talking about CP. This one, we're just talking about specific heat, and this one is treated as a constant. Now, in my exam, if we have this kind of problem, I will specify in the problem saying like treated as a constant. But if not otherwise specified, do not treat it as a constant. Think about it as a function of temperature. Okay. Now let's move on to our lecture 4. So find this lecture note very short, so hopefully I can finish everything and catch up on our actual course schedule. So goals of lecture 4. Today we'll first talk about the first law of thermodynamics, and then we'll introduce a state function, enthalpy, and talk about the physical meaning of enthalpy. Getting started. First law of thermodynamics. So the full statement of the first law of thermodynamics might sound a little bit bizarre to you. So the way the textbook put it is that there exists an extensive state function, which is E. Now the total energy is defined to be the sum of Q and W in a closed system. Now if you think about it, there are two key description of this new state function we described, right? So first of all, we have extensive. Remember, what is an extensive function? It says extensive function is one whose value equal to the sum of its value for the part of the system, right? It is an extensive function, like volume, like a smaller bottle of water and a bigger bottle of water, making volume an extensive function. And energy is a state function. So by definition, a state function is saying its value only depends on the current thermodynamic state of the system. Remember, we say thermodynamic state, we're saying the macroscopic properties defines a thermodynamic state. Like two thermodynamic states that are the same to each other will have exactly same macroscopic properties: volume, pressure, temperature, and also total energy. Right? So when we say two systems are the same thermodynamic state, we're saying all these macroscopic properties and all these state functions must be the same. So when we're thinking about a process, a thermodynamic process between state A to state B, what our first law of thermodynamics says, the total energy change must equal to the heat plus the work. So when we say Q and W, we're referring to Q as the heat flow into the system. W is the work done on the system. So since we're talking about energy, there are several things that we already know, and there are ways we can simplify this energy to more thermodynamically relevant terms. So the first thing, what do we know about energy? So using our law of energy conservation, because we know energy is conserved, you cannot like create energy or destroy energy just out of nowhere. So what we're saying is that for any process, the energy of the system plus the surrounding remain constant, or the total energy change of your system plus the total energy change of your surrounding equals to 0. This is just physics, right? Very straightforward. The next statement we have is talking about internal energy. So like energy, our internal energy is also an extensive state function. So what it means, we have total energy, or E, that will equals to kinetic energy, or we abbreviate it as K, or I guess I can write it the other way around, plus potential energy, plus our internal energy. So if you think about a system that contains both kinetic part, potential part, and internal part, the reality is like it's very complicated. It's a little bit hard for us to analyze. So for us, when we're talking about thermodynamics, mostly we're focusing on the internal energy of a system. Now, the nature of that internal energy rooted in the statistical mechanics or the movement of your particles and the partition functions. So we will save the nature of potential energy to the very end of this quarter. If we have enough time, we'll have an introduction to statistical mechanics and answer the question, what exactly is internal energy? But for now, let's just save it. Let's say like internal energy is part of description in like what the nature of that system is. And to further simplify it, I think this one should be closed. So let's imagine a closed system that is at rest. So there's no acceleration, saying there's no movement, right? There's no kinetic energy. And also no external field. So this is also pretty straightforward for thermodynamics. It's not hard to keep a system at rest and also no additional field that's not exercising on it. So for a closed system at rest without external field, our delta E just becomes equal to the delta of your internal energy. And this process gives us this claim that delta U equals to Q plus W. And in here, I just want to highlight that in your textbook, you will find a lot of equations, right? That's just true. There's lots of equations in your textbook. So I highly recommend you do not like jump or just grab a random equation to use. You're almost certain to get it wrong. So know what are the assumptions we're using and then link those assumptions to the specific problem we're looking at and then choose the equation accordingly. Like in this case, when we're saying, when we're making these statements, so this equation like delta U equals to Q plus W actually uses like two things, right? So the first thing is that delta E equals to Q plus W. So that is just true for any system. That's the first law of thermodynamics. And all these things, all these assumptions, we're trying to take consideration of like delta E equals to delta U. And then we have delta U equals to Q plus W. All right, so that's actually two pieces of information putting together into one equation. So that's why if you skip pages, it's easy to get lost looking at those equations in the textbook. All right. And then in here, one more thing we want to address is whenever we're putting things like delta U, we're always saying that's final minus initial. In addition, whenever we're looking at Q, we're talking about the heat of the system. All right, so a positive Q means we have heat flow into the system. And then a negative Q would mean the heat flow is from the system to the surrounding. So a typical question you might be asked is, say we have like 2 cups of water, right? So when mixing them together, the heat flows from cup 1 to cup 2. So which one of them will have a higher initial temperature? So those are the kind of questions you want to think about and know how to answer. Same applies to work, right? So when we say there's a positive work, we're saying the work is done on the system by the surrounding, and a negative work means work is done by the system on the surrounding. All right. And then taking this relationship one step further to infinitesimal processes, just using calculus, what we're seeing is the infinitesimal change in internal energy equals to the infinitesimal change of heat plus infinitesimal change of work. And that should also be like closed system, rest, and no external field. All right, so there are different variations of the first law of thermodynamics. But at the end, one last thing we want to emphasize is that our internal energy is, again, a state function. Or the other way, if we write it down, what it says is delta U, or the change of internal energy, only depend on the initial and final thermodynamic state of the system. Right, so even if my delta U equals to Q plus W, where Q and W are path integrals that we need to know their path, delta U itself, or internal energy itself, is a state function that only depends on the initial and final state of the system. And again, when we're writing delta U, we're always referring to final minus initial. So this can be very useful. For example, if we're thinking about a cyclic process, which is defined as your initial thermodynamic state equals to the final thermodynamic state. Now, what is going to be the delta U for a cyclic process? Right, so it's going to be 0 because your initial state and the final state of a cyclic process is by definition the same thermodynamic state. And because they're at the same thermodynamic state, all state functions will be the same, right? So that gives us a mean to solve for work or heat, because these are path dependent. You can't it's, for example, if I'm mixing 2 cups of water, it's easier for us to measure, say, temperature change. It's harder for us to measure how much work is being done in that process. But by manually set a cyclic process, we have a mean to calculate heat or work if we only know one of it. So for example, in this problem, we're seeing a mole of water vapor initially at 200 degrees and 1 bar undergoes a cyclic process for which work equals to 338 joule. So how can you find out the heat for this process? So this is one of the example, using what we just learned. We know that delta U equals to 0 for a cyclic process. And we also know for this system, which is it's just giving us everything, but we can assume this one is closed. Because it's just 1 mole of water, there's no exchange, there's no reaction, and at rest and not undergo any acceleration, no external field. So we can use our first law of thermodynamics, delta U equals to Q plus W. So knowing my W equals to 338 joule over Q equals to negative 338 joule. All right, and keep in mind, what does these positive and negative mean? How do we read it out? When we say W equals to 338 joule, what we are saying is the surrounding is doing 338 joule of work on the system. And in the same time, because it is a cyclic process, the system is transferring heat, or the heat is flowing from the system to the surrounding. And the total internal change of internal energy for this process, for the cyclic process, equals to 0. All right. Okay. Next question. This one is a sample exercise problem. You can also find the answer key in your textbook and also in our annotated note. So this is asking you to calculate Q, W, and delta U. So in this question, we're giving you information like specific heat of water and also keeping that as a constant. So we have a way to calculate for heat, like Q equals to Cp H2O, assuming it is constant, times T final minus T initial. And at the same time, we have a way to calculate for work. So that equals to negative PdV from V1 to V2. We don't know V, but we have mass and also densities of water. And you can calculate both heat and also work. And adding them together, we have a way to calculate for delta U. So leave the algebra to you. But before we move on, let's look a little bit more into these conceptual questions. So these are the true and false questions from your chapter end problems. Again, you will have true and false problem in your discussion worksheet and also in our exams. So let's just go over it and see how to approach these problems. All right. I'm going to cross this problem C out. So this one is a little bit unfair for you because we haven't talked about entropy. Let's just focus on A, B, D, E, the 4 true and false problem. First one, for every processes, the change of energy in the system always equals to the negative of the change in energy of the surrounding. Just think about it, and we'll do a quick poll in what do you think? Okay, so raise your hand if you think it is true. All right, raise your hand if you think it is false. Okay, so for people who think it is false, it's good to be cautious because whenever you see something say like for every processes, you need to be cautious, but this one is a true statement. So this one is the equation 2.38. Remember we say that delta E system plus delta E surrounding always equals to 0. So that's the conservation of energy. We can't just destroy energy or create energy from nowhere. Second one, for every cyclic process, the final state of the system is the same as the initial state. So raise your hand if you think it is true. Okay? Raise your hand if you think it is false. And you can't decide, right? So this one is true because when we talk about cyclic process, remember the definition of a cyclic process is by whether or not its initial state and the final state are the same thermodynamic state. So this one is by definition true. And you can find that full definition of cyclic or processes at the bottom of your page 49, just for your reference. Now, C, I crossed it out because when we're looking at surrounding, it also depends on whether the cyclic process is reversible or irreversible. But we haven't talked about entropy yet, so this is a little bit unfair. So let's move on. For D, for a closed system at rest with no field present, the sum of Q plus W has the same value for every process that goes from a given state 1 to a given state 2. So how do we read it? Now, in this case, this is a good example of, this is a very long statement, but effectively, let's just write it out. It's something we know. So for a closed system at rest and no field, what do we know? We know that energy equals to K plus V plus U. So this is just true, right? So that's the nature of total energy. That's how we write it out. But at rest tells us our K is 0. No field tells us our potential energy is 0. So our total energy will equal to our internal energy. And we have our first law of thermodynamics, which is delta E equals to Q plus W. So taking it together, this question fits or check the box of all the assumptions we made. So we have delta U equals to Q plus W. And this process basically tells us, okay, so Q plus W is the delta U. And we know delta U is a state function, or internal energy is a state function. And thus this statement is true, because for every process from state 1 to state 2, as long as we specify state 1 and state 2, it doesn't matter which path we take. It is a state function. Or the other way to put it, this question is asking us, is internal energy a state function or not? And the answer is yes. All right. And the last one, it tells us like if system A and B consists pure liquid water and 1 bar pressure and gives us temperature A is larger than temperature B. Ask us whether or not the internal energy of system A must be greater than that of B. So this is a very interesting question because it looks very true, right? We know that delta U equals to Q plus W. And imagine we're mixing these two systems, you know where the heat is going to flow. It's going to flow from the higher temperature to the lower temperature. However, in this process, we have no clue about what is going to be the work whenever you're mixing these two systems together. We only know, like in this case, we only know what Q is. We only know what's the sign of Q when we're mixing these two systems together. And in this case, we do not know anything about the work for that mixing to take place. And as a result, we cannot conclude on how that delta U is going to be for your system A and B. All right, so just keep in mind, we have like 3 things, right? You want to know at least 2 of them so that we can use our law of thermodynamics. But in this case, we only know 1 of the 3 things, so we can't make any conclusion. So this one is false. All right. Any questions on the first law of thermodynamics? The essential of the first law of thermodynamics is to get you familiar with the concept of state function. Now, your state function is related to path integrals Q and W, but the state function themselves are only cares or only describes thermodynamic state. And then, in addition to our internal energy, remember the first law of thermodynamics is we claim there exists an extensive state function, internal total energy, and later on we related total energy to internal energy. The first law of thermodynamics gives us a way to define energy. And then we want to extend that to new state functions. So in this case, enthalpy is the new state function we defined. So this is by definition true. So whenever you see we write like straight lines, it's just like by definition, this is true without any condition. So H equals to internal energy plus PV. Now P is your pressure, V is your volume. And before we move on, it's always nice to do a sanity check. Remember, you can only add and minus 2 terms when they have the same dimension. Right, we know that U has the same, well, it's an energy, so it should have the dimension of, or unit of joule. PV, so your pressure is Newton over meter square. Volume is meter third, so that gives you Newton meter, or effectively the same dimension as joule. So we're happy, right? So PV and your U all have the same dimensionality. So what exactly is enthalpy? We define the state function. What exactly is enthalpy. Now, that goes to the physical meaning of enthalpy. So in order to illustrate the physical meaning of enthalpy, we need to think about a special scenario where it's a reversible isobaric process. In a closed system. So remember, this one is just generally true. It's just by definition true. But in order to get an idea about what is enthalpy, we want to look at a reversible isobaric process in a closed system. It doesn't mean enthalpy is only defined for isobaric reversible processes in closed system. All right. So let's think about it. What do we have? Now we have two different tools. The first toolbox is the definition of enthalpy, which we will use later. The second tool we have is the first law of thermodynamics. So in this case, what we have is delta U equals to U2, which is our final state, minus U initial equals to Q plus W. That's our first law of thermodynamics. And I should say at rest and no field. And there are things we can further write out. For example, we know this is a reversible process, so our, and also isobaric. So isobaric, we can write like Q at constant P. So again, subscription P tells us it's at isobaric processes, minus integral of V1, V2, PdV. So this one just uses work reversible equals to negative PdV, right? And since this is an isobaric process, P is a constant, so we can take P out from the integral. Again, keep in mind, we can only do that because we say this is an isobaric process, so we know P is a constant. And this equation thus becomes QP minus pressure times V2 minus V1. Or on the left, we have U2 minus U1. So let's move the terms a little bit. So we have QP on the left-hand side, and U2, U1, and P1, PV1, PV2 on the right-hand side. So this becomes U2 minus U1 plus PV2 minus V1. Or moving the 2 with 2, 1 with 1, what we have is that QP equals to U2 plus PV2 minus U1 plus PV1. And using our definition of enthalpy, we get it to be QP equals to H2 minus H1, or the change in enthalpy. All right. So now if you think about this whole process, what we did is we defined a new thermodynamic state function. We'll come back and talk about why do we need it in our next lecture. Again, the whole point here is we want to know more about the thermodynamic state. And these are thermodynamic state functions that's going to remain the same to help us define what is a thermodynamic state. And the physical meaning of enthalpy as a thermodynamic state function is that it tells us information about the heat transfer at constant pressure. And that is the physical meaning of enthalpy. type of question we will encounter in this part, since we're talking about definition and physical meanings, are like these kind of true and false problems. So again, let's look at it together. Right, so the first question asks, the quantity H, U, PV, delta H, and P delta V will all have the same dimensions. Give you a little bit minute thinking about it. All right, what do you think? Raise your hand if you think this is true. Okay, raise your hand if you think it is false. Yes, so this one is true. And again, in our question, remember the definition of enthalpy. We have H equals to U plus PV. So we know like H, U, and PV all have the same dimensionality, right? And delta H is just the H final minus H initial. So delta H must have the same dimensionality as your H, and the same as P delta V, right? So P delta V is P times V final minus P times V initial. So because it's all like plus minus to each other, they must have the same dimensionality. And what about B? So delta H is defined only for a constant pressure process. Okay, so raise your hand if you think this is true. And if you think this is false. So this one is not true because H is generally defined as internal energy plus PV. All right, we rationalize the physical meaning of enthalpy at constant pressure. It doesn't mean H is only defined at constant pressure. Okay. About the last one. For a constant volume process in a closed system, delta H equals to delta U. So this one takes a little bit more effort actually writing down equation. Like what we know about the relationship between enthalpy and internal energy. Again, we have H equals to U plus PV, right? So if we're taking the differential on both ends of this definition, we got dH must equals to du plus dPV, or that equals to du plus pdV plus vdP. Right, so this one is just writing out the differential of the product pressure and volume. So what does it give us? When we're reading it, at a constant volume process, we have dV equals to 0 for constant volume. But your dH, well, equals to du plus vdP. Right, so taking the integral on both ends, now we have delta H equals to delta U plus integral of vdP. So this statement is not true because we have this term of the integral of vdP present. All right, so these questions are not hard. We're not using anything exceed the basic fundamental calculus we discussed, but just keep in mind how to use it. Like, for example, in this case, how to take the differential on both ends and then write out this relationship and realize, oh, my dP is not 0, so we can't say they are the equal. All right, so in our Wednesday and Friday lecture, you'll see I combine our lecture 5 and 6. So these two will be further application of the first law of thermodynamics, we'll first talk about now we have internal energy and enthalpy, right? How do we measure the relative change of internal energy with respect to temperature, or the change of your enthalpy with respect to temperature, etc.? What kind of experiment do we need to measure these changes? Because we care about how does the internal energy change with respect to temperature. And then we'll use our knowledge to solve for like what is the enthalpy change for a given thermodynamic process. So my Wednesday and Friday lecture will be more like doing problems together. So I do want to make a quick poll. How many of you want to have like a printed out blank note so you can directly write on there when I'm writing on there? So raise your hand if you need a copy. I just want to know how much copies I want to print. Okay, I only need, so I'll only print like 10 copies. If you don't have one, okay, good luck. But nevertheless, I'll print like 20 copies. So Wednesday and Friday, we will be working on those problems and applications together.